Hello again. In this video lecture we will learn about how to determine the material properties through a very simple laboratory test. And this test is known as the tension test, which, as I said, it's commonly used in the laboratory to determine the mechanical properties of various materials. So we will see now how we can use this test and what exactly we will test and what measurements we will do in order to be able to determine the material properties of materials that we need to know. So in this test, a special specimen is machined from the material to be tested. The specimen looks like so. It's, as you see, widened up at the ends. It looks like a bone, really, so that's why in jargon is termed a dog bone specimen. But the wider areas of the specimen are necessary so that the specimen can be clamped in the testing machine, which will then apply a tension force, an axial tension force on the specimen, P, as shown. Now the machine will measure the applied force, so we can have a record of that, but we also need to know the elongation of the specimen. So this is done by attaching a special gauge that can measure very precisely very small minute elongations, and the gauge is attached to the specimen before the specimen begins to be loaded by force over a special length which is called the gauge length. So this would be the original unstretched length of the measuring or measured area, and typically this is in the order of 50 millimeters. Now this test is given in test standards, so it's a standard test, and all the dimensions of the specimen and of the gauge length and so forth are strictly specified in the standards. Now remember that the stress equals to the axial force divided by the cross-sectional area, and as I mentioned, the axial force will be measured by a load cell of the machine which the machine is fitted, and the cross-sectional area is the area of the test specimen within the gauge length in that 50 millimeter area of the specimen where the measurement is being done. Now secondly, do remember that the strain is equal to the elongation divided by the original length, in which the elongation in this case will be obviously measured by the gauge that is attached to the specimen, and L is the original length, and in this case L will be the 50 millimeter gauge length, which is the original unstretched length of that portion of the specimen. Now having said that, we're measuring again P and delta L, and then hence we can calculate sigma and epsilon, the stress and the strain, and we can represent the measured value on a graph like this. And for steel, for example, this is what we'll get. Initially, a very steep portion from O to A, so from a stress of 0 to a stress that we will term sigma yield, and the corresponding strain for reaching sigma yield is really very small. It's in the order of 0.15 to 0.2% of strain. Now the slope of this portion is actually an indication of the modulus of elasticity of this material. So by determining the slope, we can determine the modulus of elasticity of the material. So here are two very important parameters that we determine: the modulus of elasticity and sigma yield. Region OA is considered to be linear and elastic because you can see the material behaves linearly, and if we unload the material from point A to O, it will unload on the same line, so we will reach point O with no permanent deformation. So the material is also elastic. Again, OA, linear elastic area. Now, beyond point A, if we keep on testing the specimen, all of a sudden the specimen will experience an yield plateau in which deformations will be very large with minimal or no increase in the actual stress. And that will happen until a strain of about 10 times the strain corresponding to the yield stress, in the order of 1.5 to 2% of strain. Now, if between A and B we unload the specimen, say from point C, the unloading will also be linear, and you can see that we will recover a little deformation between D and E, which is the elastic component of the deformation. However, we will end up with a permanent deformation between O and D, which will never be recovered. So hence, beyond point A, the material does not behave fully elastically anymore, but it behaves predominantly plastically. After point B, the molecules in the material will line up, sort of like the soldiers facing an enemy, and the material becomes a little stronger, and it will be able to gain more strength and develop a little more stress up to point F, which is the maximum stress that the material can develop, which is termed the ultimate stress. The area between B and G is called strain hardening, or in other words, the material hardens because of the large strain that it's undertaking. At point G, at the end, the material will fracture at very large strains in the order of 15 to 30% of strain. Now, between F and G, you will see that there is a decrease in stress, and this is not a real decrease in stress, but it's happening because of a phenomenon called necking down, in which the cross-sectional area of the specimen will become much less than the original cross-sectional area as the specimen stretches a lot. But we cannot actually measure this area, so we will always divide the applied force by the original cross-sectional area, and hence when we calculate the stress, we will end up with a decrease in stress. Now, if we unload anywhere between B and G, say like from point H, we will get a similar type of unloading as in the plastic area or yield area between A and B. So the material will have a small elastic component, but it will deform predominantly plastically. What is important to note is that for a structural perspective, we consider the material has failed at or after it reaches sigma yield. And the good thing about this for a material like that is beyond that there are very large deformations between sigma yield, the yield stress, and the ultimate stress. And this is termed a ductile behavior, which is typical to some metals like structural steel, aluminum, and other types of similar materials. And it's a very good type of behavior because it will give us warning. We will see that some structures might experience very large deformations So it means we have exceeded the yield stress, and that means the structure is in distress or in imminent danger of collapse. So we're going to run away out of it. So therefore, ductile is a very good property for a material. Now, other materials might experience a different type of stress-strain relationship, like for example the one that I'm drawing here, in which fracture occurs at very small values of the strain, for example something between 0.2 and 0.3%, and the corresponding stress is called this time just sigma ultimate. There is no real yield stress anymore. The material will fail very quickly. And you will see from this diagram that the behavior is mostly non-linear, as OA is not a line, except for a very small initial portion close to the origin. And the tangent to the curve at that origin will give us the initial modulus of elasticity. So if we determine that slope, we can determine the Young's modulus from that slope. Other than that, the behavior would be generally nonlinear and with some plastic deformation component as well. What is typical for this type of curve is that this material experiences very small deformations before failure, and hence the material will fail quickly without any warning. This is termed a brittle behavior and is not as beneficial as the ductile behavior because it does not give warning before it fails. Some of these materials are, for example, concrete, cast iron, stone, glass, or if you want to play an experiment when you are next time in a classroom for another course, you can also play with a chalk that you used to write on the blackboard, and that is another example of brittle material. Now, for the purpose of our design, please note that the ultimate stress can also be termed sometimes as the allowable stress or the failure stress and so forth. And from the point of view of the failure of material, for ductile materials, the yield stress, or for brittle material, the ultimate stress or the allowable stress or the failure stress mean the same thing. So this is about this interesting laboratory test that helps us determine the properties of the material. So thank you very much for watching this lecture, and I will see you again at the next one.